So my name is JayPark, and for my capstone project, I conducted a stratospheric balloon landing suitability analysis in Arizona for the company that I work for, Worldview Enterprises. So stratospheric balloons, also known as high altitude balloons, are an atmospheric research platform that's gained popularity in the past century. And Worldview is an aerospace company based in Tucson, Arizona that specializes in building and operating a steerable high altitude balloon platform called the Satellite. And now these satellites can weigh up to 1,000 kilograms or over 2,000 pounds. And there are several advantages that exist for stratospheric balloon um, over traditional satellite when it comes to data collection. The first advantage being their cost effectiveness. So it is much cheaper to build a stratospheric balloon rather than a traditional satellite. The second advantage is their ability to capture data at a higher spatial resolution due to their proximity advantage to Earth's surface. And lastly, or the third advantage is their ability to loiter over a specific area for extended periods of time, allowing for continuous data collection and temporal analysis not possible with a typical traditional satellite. So there is a challenge that exists for flight operators at Worldview for every stratospheric balloon operations, and that is selecting and evaluating landing areas. And this challenge becomes especially tasking during emergencies when operators lack sufficient time to fully assess these areas. So this study aimed to tackle this challenge. So the study area for this project was the state of Arizona, which is one of the primary areas of operation for Worldview Enterprise. And Arizona covers approximately 130,900 square miles, and it is comprised of very diverse landscape from the open desert in southern Arizona to mountainous forests in northern Arizona. So the flight operators at Worldview consider four landing criteria when determining landing areas. They are population density, airspace, power line proximity, and gap analysis code status code, or gap analysis project status code, or GAP project. And GAP is a national program managed by the United States Geological Survey that identifies areas where conservation efforts are needed to maintain populations of common species. And USGS assigns four different gap status codes to conservation areas that reflect the level of protection and management intent. So gap status code 1 designates areas with permanent protection and mandated management plan to maintain natural conditions, while a gap status code 4 designates areas with no known legal or institutional protection. The population density dataset that was used for this study was downloaded in a comma separated values or CSV file. The airspace dataset was downloaded in a polygon vector shapefile, and it was comprised of two datasets, one being special use airspace and the other being the class airspace. The power line dataset was downloaded in a line vector shapefile. And lastly, the gap status code dataset was downloaded in a polygon vector shapefile. So this study tackled the challenge that I mentioned earlier by answering these research questions. One, how much influence should a criteria have over other criteria in case of emergencies? And two, where are the suitable landing areas in Arizona determined by a weighted suitability model? So my study consisted of a seven-step workflow. The first step in the workflow was to acquire all external data sets, flipping them to the extent of the study area, and then projecting them to a common coordinate system, which in this study was the NAD 1983 UTM Zone 12N, which is the typical coordinate system for a study extending to the entire state of Arizona. The next step was to determine criteria weights using the analytical hierarchy process and to determine suitability score within subcategories of each criteria. The third to the sixth step was to prepare the criteria datasets by converting them to raster data. And last step was to construct a suitability model using the raster criteria dataset or layers, applying the weights derived from the survey and transforming them with the corresponding functions within the modeler to generate the landing suitability map. So the analytical hierarchy process is a decision-making framework that allows qualitative data to be quantified to numerical weights. And this is done so through a pairwise comparisons between each criteria. So I conducted AHP for this study by through a survey that I created on Survey 123. And part one of the survey asked the respondents to compare the relative importance between each criteria and the strength of that preference over that criteria. And this survey was disseminated to the stakeholders, which in this case were my coworkers, Worldview's flight operators. Part two of the survey asked each flight operators to assign landing suitability within subcategories of each criteria. So in this image you see right here is the section of the survey asking the flight operators to assign suitability to different types of airspace. The not allowed choice was converted to a suitability score of 1. The allowed but avoid if possible was converted to a score of 3, and highly suitable was converted to a score of 5. This process was repeated for gap status code suitability. And as for the power line proximity suitability, the survey asked for the distance from which flight operators deemed as not suitable, suitable, and highly suitable. These survey results were then imported into Excel into an AHP matrix and averaged for weights and scores. So within the suitability modeler, the population density raster dataset was transformed with continuous functions. Cells with population density of less than 3.9 persons per square kilometer was assigned a suitability score of 5, and cells with population density greater than or equal to 3.9 persons per square kilometer was assigned a score of 1. And the number 3.9 comes from the standard population density limit that Worldview considers for landing areas. The airspace raster dataset was transformed with unique categories, and each type of airspace was converted to a suitability score from the result of the survey. The gap status code suitability was also transformed with unique categories, and each gap status code was converted to a suitability score as the result from the survey. And lastly, the power line proximity was also transformed with unique categories, and the distance from power line was converted to suitability score determined from the survey. And these are the criteria we determined for each criteria from the AHP survey. Based on the average responses from operators, it was deemed that population density shall weigh 46%, airspace 21%, gap status 17%, and power line proximity 16% for the landing zone suitability calculation. And these are the results of the suitability score of subcategories within each criteria. So for airspace, it was deemed that our Class B, prohibited, restricted, and wilderness area assigned a suitability score of 1. Class C and D assigned a suitability score of 2. Military operations area, or MOAs, assigned a suitability score of 3. Class C, score of 4. And Class G, which is the uncontrolled airspace, assigned a suitability score of 5. As for power line proximity, it was deemed that areas that are within 1.3 nautical miles of a power line is not suitable for landing. Areas at least 3.4 nautical miles were suitable for landing, and areas beyond 6.4 nautical miles of a power line were assigned highly suitable or score 5. As for the gap status code suitability, responses from the flight operators were unanimous, where they said that areas that are assigned gap status code of 1 and 2 have a suitability score of 1, and areas assigned gap status code of 3 and 4 have a suitability score of 5. And this is the landing suitability map generated from the suitability model. So with the given criteria and weights, the map displays majority of Arizona as highly suitable landing areas. And I converted the number of cells to surface area and calculated 23,697,500 hectares of highly suitable landing areas within Arizona. So there are two key takeaways from the study. The first key takeaway is that population density influenced landing suitability 2 to 3 times more than other criteria. And this is in line with the worldview's operational philosophy that public safety is the #1 priority when it comes to stratospheric operations. The second key takeaway is that the largest highly suitable landing areas exist in northwestern Arizona in the Mojave and the Coconino counties. There is a limitation to the resulting suitability map, and it is that it should only be used in case of emergency terminations. And this is due to the fact that during a nominal termination, worldview flight operators search for areas that have a that have a suitability score of 5 in all criteria, meaning they look for areas that have a population density of less than 3.9, or at least 6.4 nautical miles away from power lines, is in a gap status code of 3 and 4, and falls under a Class G airspace. However, with that being said, the resulting suitability map is still useful in case of emergency terminations to maintain public safety. And that is all for my presentation, and I open the floor to any questions that you guys may have.